Let's check out what's happening in section 2.7, inverse functions. As you can see, the learning objectives are we're going to find the inverse of a function informally, verify that two functions are inverses. We'll look at graphs to verify that two functions are inverses of each other. We'll use a horizontal line test to determine if a function is one-to-one. And finally, find the inverse functions algebraically. So let's recall from section 2.2. A set of ordered pairs can represent a function if each x corresponds to one y value. So, like in this pairing, 1 pairs with 5, 2 pairs with 6, 3 pairs with 7, 4 pairs with 8. That made it a function. Now, what we want to do is interchange the first and second coordinates, which means the 1, 5 will now become a 5, 1. So we're going to interchange those coordinates. This would become a 6, 2, 7, 3, 4, 8. By interchanging those, what we're doing is we're forming an inverse function. So an inverse function maps a y to an x. And the notation for an inverse function is f inverse of x. So the inverse function of x plus 4, which gave us this set of ordered pairs, the inverse of that will be x minus 4, that gives us this set of ordered pairs. That would be our inverse function, and it maps the y to the x. I want you to notice that by reversing the x and y coordinates, going from 1 to 5 and then 5 to 1, we're actually reversing the domain and range. So the domain of the regular function, f, becomes the range of the inverse. And the range of the inverse becomes the domain. The range of the original function becomes the domain of the inverse. So if the domain looked like this, then that domain becomes this guy's range. So they're switched. So we're kind of swapping out x's and y's, which means we're going to swap out domains and ranges. So this range was 5, 6, 7, 8. This domain is 5, 6, 7, 8. So notice how those two guys switch. Another thing that we can notice, or as that's going to happen, is when we do the composition, very important, when we do the composition of f and f inverse, we will always come up with the identity function, which means we come up with just an x. So let's look at that composition. This part right here is basically f circle f inverse, and this one is f inverse circle f. We're just doing the compositions, which means we're placing the inverse inside the original function. And the original function was what? X plus 4. So we're taking x minus 4 and putting it into x plus 4. And when we do that, those two 4's cancel and we're left with x. Well, when we do the same thing, but we do f inverse circle f, that means we're putting the original function into the inverse. And the original function was x plus 4. And if we put x plus 4 into x minus 4, the two 4's cancel and we end up with x, our identity function. That's going to always happen when you compose a function and its inverse. If you want a visual of what's happening, then let's take a look at this. I've got my regular function that maps an x to a y, a domain to a range, and the inverse goes backwards and maps basically a range value to a domain value. So the regular function goes this direction, the inverse function goes in that direction. So some of the properties of an inverse function are these. If you have the ordered pair AB on the function itself, it will become the ordered pair BA on the inverse. Also, the domain of the original function becomes the range of the inverse, and the range of the original function becomes the domain of the inverse. last property, when you do the compositions of f and f inverse, it will always equal the function x. So that's what we're looking at. So we've got those properties that we're going to use in determining if we have inverses, what they look like, what happens with domain and range, and ordered pairs. So let's start with finding an inverse function informally. This means you're just trying to figure out, excuse me, what operation undoes the original operation in the function f of x. So if f of x, let me get my pen here, if f of x takes an x and adds 5, what is the opposite or the inverse of adding 5? Well, it would have to be subtracting 5. That would be the inverse of x plus 5. If I had a function x divided by 7, what's the opposite or inverse of dividing by 7? It would be multiplying by 7. So the inverse would be 7 times x. We would multiply by 7. So a division of 7 becomes a multiplication by 7. And addition of 5 becomes a subtraction of 5. And we can think of other operations. Suppose my original function had an x squared in it. What's the inverse of x squared? What undoes an x squared? A square root. What if my original problem had a cube root of x? What undoes a cube root? An x cubed. So we're thinking about those that undo each other. So here's a question. Which function would be the inverse of this one? So let's take a look at this original function, and we're going to figure out which of these two, whoops, where did I go? There we go. We're going to figure out which of these two, g or h, would actually be the inverse of f of x. Well, let's take a look at what happens in f of x. I see that I have a division of 7, and I see that I have an addition of 4. How could I undo both of those? That's not an addition, Melissa. That's a subtraction. Sorry, guys. I was thinking inverse. This has a subtraction of 4. This has a division of 7. So that means my inverse would have to have an addition of 4 and a multiplication of 7. This would be my inverse function because it has those two inverse operations. It has an adding of a 4 and a multiplication of 7. Okay, now, not every function has an inverse. Only certain types of functions will have an inverse, and that is what we call a one-to-one function. So only one-to-one functions will possess an inverse, and a one-to-one function must pass the horizontal line test. Remember, we use the vertical line test to tell if an equation was a function. Now we're going to use the horizontal line test to tell if that function is what we call a one-to-one. So we're looking for horizontal line tests. So horizontal line test, a horizontal line crosses through that graph at more than one point, so it's not a one-to-one function. This guy over here, if I draw horizontal lines, each horizontal line crosses at only one spot, so this guy is a one-to-one function. Look at number 2 in the middle. If I graphed him, remember that square root shape is an arc. So it's an arcing shape. If I think about that shape, it would pass the horizontal line test, so it is one-to-one. Think about the shape of x squared. X squared is a parabola. So if I looked at the entire parabola, it would not pass the horizontal line test because a horizontal line crosses at more than one spot, so it's not one-to-one. So the key is our function has to be one-to-one because only one-to-one functions will possess an inverse. So the final property of a function and its inverse is the fact that the graph of f of x and its inverse will be symmetric about the line y equal x. Let's investigate that. Okay, so I have a function. It's graphed here. It goes to the point -3, 0 and the point 4, 4. Whoops. So it goes through this point and this point. So those are the 2 points on my graph. And what I've also graphed is this line right here that I'm kind of designating red. That's my line of symmetry, y equal x. So if you folded this graph along that origin, you would get this dotted line, which is our line of symmetry. Okay, so I've got the original function graphed. I've got f of x. So let's see what f inverse of x would look like. Since it's going to be symmetric across this red line, and we know about ordered pairs. Remember, we said the ordered pair AB becomes BA on the inverse. So this ordered pair -3, 0 becomes 0, -3 on the inverse, which would be right here. Notice it's across that line of symmetry. There's 0, -3. The point 4, 4 would become, if I switch x and y, the point 4, 4. So 4, 4 is on my inverse. If I connect the dots with those two points, notice that this green line would now be my inverse. And if you folded your page along that dotted red line, the two would be symmetric. They would match up. So a function is inverse has its symmetry across that line y equal x. You may not always be able to tell by looking at a function what the equation of its inverse actually is. So here is how we're going to find an inverse function algebraically. We're going to first use the horizontal line test to make sure that it is 1-to-1. In the equation, we're going to replace f of x with y. So we're going to go back to our old notation. Take out the f of x and put in a y. Then what we're going to do is interchange the roles of x and y. So that means I'm going to swap out x's and y's this way. So interchange x and y, we're swapping out x and y. Then we need to solve for y. So let's take this equation and solve it for y. So to get y by itself, I'll bring the 3 over. I'll subtract 3. And then to get rid of, there we go. Ooh, that got messy. To get rid of the -5 times the y, we do its inverse or opposite. That means we're going to divide by -5. So I interchange the roles of x and y. I've solved it for y. So this looks like y equal to x minus 3 over -5. Not too bad. And the final step is to replace that y with f inverse of x, because once you solve it for y, you have found the inverse. Okay, so I'm going to replace this y with f inverse of x. So f inverse of x is equal to x minus 3 over -5. We could also maybe rewrite this as negative x over 5 plus 3 over 5. Just breaking that up, x over -5, -3 over -5 into 2 pieces. Either way, either one of these would be fine, this form or this form. So let's try it again. Looks like I'm running out of time on this video, so the next video will pick up with problem number 2.